actually doing Compton effect and its applications in astrophysics. So Compton effect is actually extremely important. So Compton effect is actually extremely important, and it is, you see Comptonized spectrum in black hole X-ray binaries and in neutron star X-ray binaries, and also you detect galaxy clusters at high redshift using Compton effect. So I'm actually just going to show you some astrophysical examples of Compton effect before moving on to the next topic, which is basically the propagation of electromagnetic waves through a plasma medium. So let's see. So this is where I will start. Okay, so so you can see the slides that I am sharing, right? You can see what I'm. Okay, so this is what I wanted to show you. So this is actually like a rather simple modeling that is very popular when it comes to modeling non-thermal emission from sources such as radio galaxies and other sources which show, like GRBs, which show non-thermal emission. So what you see here is this equation, this dou T of n gamma plus dd gamma of gamma dot n gamma. So this is a very simple equation which you can construct for how the distribution function of relativistic electrons, right? So this dn n gamma going like gamma to the minus p, how does that evolve in presence of different cooling losses and escape and some injection of this source term? So this is an extremely simple equation. So n gamma is a function of gamma and time. So this is a PDE, partial differential equation, where n gamma is a function of gamma, the relativistic gamma, and time. And you want to see how this number of electrons between gamma and d gamma varies as a function of time. So the left hand side is just how much does n gamma change. So this is just like a right, so let me just write down. So I want you to be able to see both what I'm writing and this screen. So just a sec. So one zone model for evolution of relativistic electrons. Okay, so you have this n gamma d gamma is the number of electrons per unit volume with their relativistic gammas in this range. Right, so this is sort of like a Boltzmann equation. So n gamma, which is a function of gamma and t. So so you consider gamma, and you consider n gamma d gamma as the number of electrons here. So what is happening? So so this n gamma can change. So tau by tau t of n gamma plus tau gamma. So now this is just a function of two variables. So this is gamma dot n gamma is equal to the source of injection of electrons in this and in this gamma. So this is some sort of a source, say some shock acceleration or something, injects electrons in this gamma range, and then there is minus n gamma by T escape, and there is some sort of an escape mechanism, for example, diffusion out of the volume of interest. So this one zone model is basically modeling some volume, and the cosmic rays or electrons are sort of leaking out of this system, and the time scale for that is this T escape. The cosmic rays are also being injected, and this is the source term as a function of gamma. Now so if you don't have these two, no source, no escape of particles, then the rate at which the number of electrons here in this bin in gamma changes is just because of cooling, right? So gamma dot is equal to d gamma dt, right? And this is just related to the cooling, which is equal to gamma divided by T cool, right? And you can have cooling of these electrons due to synchrotron losses and inverse Compton losses. So you can have T cool is equal to the minimum of the two, minimum of the T sync, T inverse Compton. Okay, and we know that the synchrotron cooling time scale is equal to gamma mc squared, and this is electron mass, divided by 4/3 sigma T C U B gamma squared, right? And T inverse Compton is equal to gamma m e c squared by 4/3 sigma T C U P H gamma squared. So so here we show an example of how this spectrum, right? So we know, right? So this, let me just write down. So n gamma is proportional to gamma to the minus p is something that we deal with, right? So this is like the injection spectrum. So what we are saying is S gamma is equal to some constant times gamma to the minus p. This is how the cosmic rays are injected. So if your cooling losses are negligible, that is, gamma does not cross these bins, the electrons don't cross this gamma bins because of cooling. In that case, this term gamma dot is 0. So, and if you're considering steady state, so the right hand side is 0 in steady state. So what you have is n gamma in steady state is equal to S gamma T escape. It makes sense. If you have this volume in steady state, whatever losses happen for these electrons have to be compensated by whatever injection happens. So, and T escape is independent of gamma. So you get n gamma in steady state is proportional to gamma to the minus p. That is what we assume, right? Now, if in addition to this we have losses, and we can actually consider two cases. One case we can consider is when S gamma is equal to 0. So in this case, what you have is some initial n gamma versus gamma. So you have some initial gamma to the minus p distribution, but because of cooling, what happens is the high energy electrons just get cut off. So these are 3 different times. So this is increasing time. So if you wait for a time of order T cool, right, all the electrons which have higher gamma than that, right, you see the cooling time is shorter for higher gamma for both inverse Compton and synchrotron. So you develop this sort of a exponential cutoff at gamma, at a value of gamma for which the cooling time for which the age of this system is equal to the cooling time. And what happens to the spectrum? This is for n gamma. What happens to the spectrum? We know that spectrum epsilon epsilon nu is proportional to nu to the minus p minus 1 by 2, right? We saw this for synchrotron and also for inverse Compton. If you have a constant frequency of seed photons. So this is your epsilon nu. So this is in gamma space, so this is epsilon or flux space. What happens is you have gamma, so nu to the minus p minus 1 by 2. And as soon as you reach this cutoff frequency, there is a cooling cutoff, beyond which you don't see any photons. Okay. So this is the case when there is no injection. That is, you just had an initial distribution of particles and then they just cool off with time. Now we can have another case where you have, so this is one. The other case that we can actually consider is when you have continuous injection. So in this case, what happens is S gamma is not equal to 0, right? And so what happens? So let's consider the same n gamma versus gamma situation. You have gamma to the minus p, right? So in absence of cooling, your S gamma, so you have this situation, you have this, right? So in absence of cooling, you also get a gamma to the minus p in steady state, right? Now what happens in this case if you have cooling, right? So you try to distinguish. So this was S gamma equal to 0. You only had a, somehow you created these electrons at t equal to 0 and you let it go. Here you are continuously, injecting particles with this gamma to the minus p. Now, what happens is this, what will be the effect of cooling on this situation? That's the question. So, so S gamma equals n gamma by t escape, right, in steady state. So you are considering dou t equal to 0. Now we again consider steady state, but gamma dot is not equal to 0. Basically allow cooling losses. What happens in this case? If you have cooling losses, then this term, right? So this dou gamma dot n gamma sort of scales as n gamma by gamma, and gamma dot goes like gamma squared. Right, so gamma dot goes like 1 by gamma squared. Sorry, 1 by gamma, not gamma squared. There is a gamma there, and there is a gamma here. So this goes like 1 by gamma squared. This whole thing goes like n gamma by gamma squared. Whereas this t escape is independent of gamma. So basically what it means is that the cooling losses dominate escape, right? Escape for high gamma particles, high energy particles. So what does that mean? That means that so then the balance in steady state will not be so. So in that case, what will happen is this term will balance S gamma rather than the losses due to escape balancing S gamma. So this gives you, I mean, if n gamma is a power law, right? So this balance gives you n gamma by gamma square going like S gamma, or or n gamma going like so basically this is the balance. And the other thing is, just a second. Right, so gamma dot is right. So gamma dot is gamma divided by T cool, T sink, or T inverse Compton. So this is equal to gamma divided by T sink is proportional to 1 by gamma, proportional to gamma squared. Okay, now I get it. Not this is. Let me erase a little bit. Right. So what happens is, so dot gamma. Gamma dot is proportional to gamma squared n gamma, right? So gamma dot is higher for higher gamma. This balances as gamma. So if we assume a power law form for n gamma, then this gives us gamma times n gamma in steady state. So assuming power laws. That is what we have assumed anyway. So this gamma gamma cancels. This is S gamma. Oops. Or n gamma is proportional to gamma to the minus 1 S gamma. So what happens is, in case where there is continuous injection of high energy particles, the n gamma slope changes by 1. Slope changes by 1 due to cooling losses. So this break actually again happens at the same location where T is equal to T cool. Okay, so with time it moves to the left. But the difference from the previous case is that here there was no particles with gamma higher than the value of gamma for which cooling time is equal to the time, the age of the system. But in this case, there is only a change of slope by 1. Okay, and this has an implication for the spectrum, because if your slope in gamma changes by 1, basically your P changes by 1, so your spectral index changes by a half. So here is actually an example that shows it. So if you have like a nu to the minus 0.6 spectrum flux, okay, as a function of frequency. Now we consider two scenarios, this green scenario where there is only initial electrons which are cooling, only cooling of initial electron. This is the first scenario that I outlined. So at T equals TH, you don't have anything which at higher frequencies, electrons at higher gamma, which have a cooling time which is shorter than the age of the system. So this is the first scenario where you had injection at T equal to 0 and no continuous injection. This orange line is the second scenario where there is continuous injection and cooling. And the cooling break sort of appears at almost the same frequency, except that here, rather than just cutting off abruptly, there is a change of slope by minus 0.5. So from nu to the minus 0.6, it becomes nu to the minus 1.1. So this is called a cooling break. This is a cooling cutoff. This is a cooling break. So, this modeling is quite popular for modeling radio galaxies and, synchrotron, evolution of synchrotron emission in a lot of cases. So you will also see the effect of cooling in something called spectral aging. So let me open up something, just a sec. Spectral Index Map. Radio galaxy. So, for example, not this. Yeah. So, oops. So, this image is something called a spectral index map. So basically nu to the minus alpha. This is the map of that alpha. So you see wherever this is red, you have shallow spectrum of radio emitting plasma, and wherever this is blue or green, this is a steep spectrum. So you can actually see that there is like a gradient from red to blue as you move from this side to this side of this radio emitting plasma. So what it means physically is that some source which is energizing the electrons is located here where it is red, and as this plasma moves there, because of cooling, it undergoes this spectral steepening. Okay, it's sort of along the line of what I was mentioning, that because of cooling the spectrum gets steeper. So this is very, very popular. Making spectral index maps of radio galaxies and other objects is very popular. Okay, so good. So this was about modeling of electron populations. Any question? Hello. Any question on this material? This is actually quite practically important in a lot of astrophysical modeling. So it's good to know this simple model. It's also extremely simple actually, but it's widely applicable. No question? Okay, so then let me ask question to someone. Priyanka?
Yes, sir.
So can you tell me what I just said about what is the difference between this green spectrum and in this orange spectrum?
Sir, in green spectrum, we are considering only cooling of initial electrons. Like in this, we are considering S nu equals to 0.
Yes. And this one, minus 1.
Sir, in this, we are considering S nu is not equals to 0, and we are getting a factor of gamma raised to power minus 1 because
because of cooling of these electrons. So the balance is between S gamma and this term rather than
yes,
between S gamma and this term.
Yes, sir.
Okay, good. And why is this nu to the minus 1.1? So from minus 0.6 it becomes minus 1.1. It became minus 1.1. So this is a steepening by 0.5 for
Yes,
gamma.
sir.
Yes.
Sir, because of that gamma factor, gamma
Right.
minus 1.
5.5. Gamma minus 1. Why does it translate to minus 0.5?
Sir, because mu is proportional to gamma square.
Okay.
So, sir, by half factor.
Good, good. Okay, good. At least someone is listening. Nice. Okay, so let's go to some other astrophysical example. This is an example of Compton effect. I briefly mentioned about it. So let's see. So this is application of Compton effects to something called galaxy clusters, right? So there was a question on galaxy clusters in the exam as well, where I talked about Bremsstrahlung emission from galaxy clusters. But galaxy clusters also contain hot electrons, a large number of hot electrons, which can Compton scatter the background, cosmic microwave background, the background CMB. This effect is called thermal Sunyaev-Zeldovich effect, right? So this is the scattering of the background, cosmic microwave background. So you see this is intensity as a function of frequency, and this dashed line is the CMB spectrum in this frequency range. Okay. Now what happens is, in this galaxy cluster, you have electrons. So you have just a sec. So in these galaxy clusters, oops. So you have you have a galaxy cluster. CMB, radiation comes from all directions everywhere. So so when you are seeing from here, so this is a galaxy cluster. So what happens is these have electrons which are also thermally moving in all directions. All right, this is a galaxy cluster. So isotropic radiation, isotropic electrons. This is the standard setup that we did. Scattering of isotropic photons by scattering or by isotropic distribution of electrons. So temperature of galaxy clusters is like 10 to the 7, 10 to the 8 Kelvin. The CMB temperature is 3 Kelvin, right? So basically we are in the regime where K, and also KT by MC square is much less than 1, right? Because MC square is 0.5 MeV, which is 10 to the 9 Kelvin, 5 times 10 to the 9 Kelvin. So you are in the non-relativistic regime, but you are in the regime where, so epsilon, delta epsilon by epsilon, the change in energy in single scattering divided by the energy of the background photons is equal to KT by MC squared 4 KT minus epsilon of the photons, right? You have this expression. You had this expression when we did Comptonization, but this epsilon corresponds to 3 Kelvin. This is 10 to the 7, so you can actually ignore this. So in a single scattering, you get this much. This is the change in energy divided by energy, which is still less than 1 in a single scattering, because KT by MC square is small, right? MC square is 5 times 10 to the 9, KT is 10 to the 7, 10 to the 8. Okay, so what happens is, the other thing is the optical depth of these CMB photons. So it's just n sigma dl, right? So this is just n times the length, the size of the galaxy clusters times sigma Thomson. This is about 10 to the minus 3. So what it means is that only 1 out of 10 to the 3 photons get Compton upscatter. So you will have upscattering. Basically, photons will gain energy because electrons are hotter than the photons. So on average, the photons that come after scattering will have higher energy compared to the ones which came in on average. So what happens is something like this. So this is your CMB spectrum, and now the only 1 out of 10 to the 3 will get upscattered. So this arrow shows that upscattering by how much. This is a small change, right? It goes from 100 to less than 200 hertz. So the energy change is of order KT by MC squared, right? Delta epsilon by epsilon, right? That is what the change in energy per unit energy is 4 kT by mc squared. So that's about, let's say, 10 to the 8, 4 times 10 to the 8 divided by mc squared, 5 times 10 to the 9, it's about 0.1. Okay, so the shift in energy is by 0.1. Delta nu by nu is about 0.1. But only a small fraction of these photons get scattered. So the CMB spectrum will not change all that much. The reason is not all the photons are getting this scattered. Okay, so this is exaggerated. This difference in the intensity is exaggerated here, but this is a realistic value, right? So what you see is the sign is the same, right? Here at wavelengths, at frequencies less than 220 gigahertz, you see that the CMB, the galaxy cluster, the direction towards galaxy cluster appears cooler, right? The intensity has gone down. It appears cooler than the normal CMB, whereas at higher frequency, the galaxy cluster, the photons coming through the galaxy cluster have higher temperature. So this is change in temperature or change in intensity as a function of frequency. So you have a deficit and then you have an excess. And you see these are for three different temperatures. So higher the temperature, the larger the right. So this is 5.1 keV cluster, 15.3. Right. So the higher the kT, larger is the shift of energy. So you see this, this blue line goes to higher frequencies because it is higher energy. The shift is higher. Now the amplitude is lower for higher energies, and I think the amplitude of this, how much does this change from the CMB value, depends on the optical depth of the cluster, because this y-axis will only depend on how many photons get scattered, whereas the amplitude of the shift will depend on kT. So this is anyway the signature, and delta I by I is of order 10 to the minus 3. So it's a very small effect, but since we can measure the CMB so very well, this small effect is measurable. So this is the Compton Y. If you recall, we had this Compton Y parameter, which was delta epsilon by epsilon multiplied by the optical depth, right? And I said the optical depth is like 10 to the minus 4, so 1 to minus 3. So this is 10 to the minus 3 times 0.5. So the delta epsilon by epsilon is kT by mc square, which is like 0.1-ish, and the optical depth is like 10 to the minus 3. So Compton Y is much less than 1. So this spectrum is not Comptonized in the sense that the spectrum does not change much from the incident spectrum, but we are still able to measure it because we can measure very small changes in the brightness temperature of the CMB. You recall that CMB is uniform and it is at 2.73 Kelvin, but our experiments can detect fluctuations of order 10 to the minus 5, whereas this is like 1, 2, 3, 4, 10, 5 times 10 to the minus 4. So this is still very well detectable. Okay, so this is a very, very powerful technique to detect galaxy clusters and to understand the distortion of the CMB because of substructure which is present in the foreground. So all these things, how is the emergent spectrum affected due to Compton scattering, is governed by something called the Compa-Needs equation. We'll not actually do the Compa-Needs equation here, but this is so Compa-Needs equation is a Fokker-Planck equation. It's sort of like a Boltzmann equation which governs the evolution of distribution function of photons, right, when they interact with electrons due to inverse Compton scattering. And what is assumed is that kT by mc square is much less than 1. which means that delta epsilon by epsilon is much less than 1, which is the regime in which Boltzmann equation can be treated as a Fokker-Planck equation. So Fokker-Planck equation is also used for example, simulating the Brownian motion of a heavy particle in a gas, right? If you have a heavy particle moving, diffusing inside a gas, it undergoes collisions with the molecules in the gas, and because of that it gets dragged down, and it also diffuses, undergoes a random walk. So it's a similar equation except for the photons, and it also assumes that the kick, right, delta epsilon by epsilon is small. In a single step it does not receive large kicks, and that's why we can make certain approximations. So this is called thermal Sunyaev-Zeldovich effect, but there's something also called kinetic Sunyaev-Zeldovich effect, which is due to the fact that galaxy clusters as a whole are moving as a bulk relative to the CMB. So if the galaxy cluster is moving towards us, the CMB photons that get scattered, can on average gain more energy. So that is not as important as the thermal Sunyaev-Zeldovich effect, but it's important to know this Sunyaev-Zeldovich effect. So here is how thermal Zeldovich effect is used for high redshift clusters, for detecting high redshift clusters. Right, and the very important thing about Sunyaev-Zeldovich effect is that it's a scattering effect, right? It's sort of like absorption effect. So as long as you have a bright enough background, you can put your scattering cluster very nearby or very far away. The signal will be the same, right? It's based on absorption or scattering, because if you have a bright enough background source, which is the CMB, and if you put the scattering stuff wherever on the line of sight, the signal is the same. This is different from emission, right? If you have an emitting body and if you put far and far away, the flux that you observe becomes extremely small. So here is an actual example. So these are 3 galaxy clusters, okay, and the main figure shows this SZ effect. So this shows the temperature at the null. So this shows right. So this shows, say, some here. So you are measuring this direction of the sky at some, say, 200, 300 gigahertz. Okay, and this galaxy cluster appear brighter than the background sky because at high frequency you have higher flux. So you see these as this is brighter. This is still small amplitude, delta T by T is small, but still detectable. So this is a galaxy cluster, this is a galaxy cluster, this is a galaxy cluster. Note that this is at redshift of 0.17. This is reasonably nearby. This is redshift of 0.83, far away. And yet the signal is more or less the same in this SZ effect, thermal SZ effect. In contrast, in this inset, what you see is the X-ray emission. Okay, here you still see a bright X-ray emission, dimmer, almost nothing. And the reason you don't see much surface brightness from X-rays is because X-ray is seen in emission, and the farther you put a body, the lower its flux, the flux received is, and also the angular size also changes with redshift. So the surface brightness actually falls off very steeply with redshift. Like, almost if you go to redshift of 1, it's 2 to the minus 4, which is 1 by 16. So that's why you can see this dimming in X-rays, but no dimming in this SZ signal. So now I have a question for you. Suppose you want to detect very high redshift clusters, say redshift of 2. What, does this suggest to you some clue as to what you should do? So, what is the technique that you should employ for detecting high redshift clusters? Can someone tell me? Okay, I guess I will have to point out people. If people do not volunteer, I will have to ask. Manish. Manish Kumar.
Hello.
Manish, can you see this?
Yes, sir.
Can you understand the question that I asked? So, this is showing this SZ signal that it does not change much as a function of redshift, but this is in X-ray. So my question was, how would one, so does this suggest a clue to how one would detect very high redshift clusters?
सर वही जैसे हम उसको कॉस्मोलॉजी बैकग्राउंड रेडिएशन से ब्लैक बॉडी रेडिएशन जो बना था कॉस्मोलॉजिकल बैकग्राउंड रेडिएशन तो उसके थ्रू उसका असजेड इफेक्ट है उस हिसाब से जो स्पेक्ट्रम बनेगा उससे डिटेक्ट करेंगे एक्सरे स्पेक्ट्रम से नहीं कर सकते क्योंकि वो हमें विजिबल ही नहीं होगा वो हाई रेड शिफ्ट के वो इनवर्सली प्रोपोर्शनल होता है ना
Right. So basically, what you're saying is right. So what you do is look at the CMB map, okay, and you look at it at various frequencies. So, for example, here, right, it has a very characteristic signature as a function of frequency. So if you look at 220 gigahertz, where there is a null, there is no effect. If you look at low frequencies, it should appear dark compared to the average CMB. If you look at high frequencies, it should appear bright compared to the background. So if you have like a Planck map or dedicated high resolution maps of the CMB sky, then you can actually find out. See, at single frequency, it's difficult, right? It's hard to say that this is a galaxy cluster just by looking at one frequency, right? Because this can also be a hot spot in the CMB sky. But if you look at say 1, 2, 3, 4, 5 frequency bands, and if you see this spectral signature, then you are very confident that this is due to some intervening cluster, right? And if you have, if you're sure about it, then you can apply for X-ray time and look through X-ray telescopes. Okay, so that's good. Okay, so then now we are actually done with synchrotron and inverse countdown. This is actually a very, very important application. This has really changed the field of galaxy clusters a lot recently. Okay, so now what we will do is we will start with the next topic, which is yeah, thanks Manish. Now we will start with the plasma effects. So plasma effects. So the radiation that we receive here on Earth travels through ionized medium, right? We know that most of the normal matter in the universe is in the plasma effect, plasma state. So the radiation that we receive in our telescopes here on Earth is modified by the intervening ionized gas or plasma. Okay, so like for example, omega equals ck. This is dispersion. This is dispersion relation for light. K omega relation for light in vacuum. Right now, but what happens if instead of vacuum, so you have some source of radiation, but instead of vacuum you have ionized gas with positive and negative charges. This is the plasma that we are considering. So so propagation through a plasma. So let's consider cold isotropic plasma medium. So what we are trying to do is we're trying to get an analogous relation, right, when you have a plasma medium. So right, so in vacuum we know that all wavelengths, all lambdas travel at same speed, right? Whether it's X-ray photon or a radio photon, if it is traveling through vacuum, they all travel at the same speed, the speed of light. Okay, but if you have a medium, then we know that like in refraction and so on, we know that the speed becomes c divided by the refractive index, right? So so in the same way, how would the plasma medium affect the propagation of electromagnetic waves? So let's try to see this. So let's consider electromagnetic. Let's consider Maxwell's equations, and let's consider e to the minus I omega t plus I k dot x form. So so plane wave fluctuations. The standard thing that we do even for EM waves in vacuum. So let me write down I k dot E. So this is just del dot E is equal to 4 pi rho, right? So this is, now rho is the charge density of the medium. So now there is a plasma medium, then your charge density need not be 0. And the second equation, del dot B is equal to 0, remains the same. You have I k cross E. So del cross E is equal to I omega by C B. This is just the induction equation. I k cross B is equal to 4 pi by C J minus I omega by C E. So this is the displacement term, and then this is Ampere's law. Okay, so this, so the difference is rho and J are non-zero because of this plasma. Okay. So we are considering ions to be at rest, and electrons are moving, but we are considering, we are considering kT of both electrons and ions is 0. So there are no thermal motions, and we are ignoring the ion motion because ion mass, proton mass is like 2000 times electron mass. So the ions don't move for the same electric field. Electrons move much faster than the protons. So we can actually ignore ion motion altogether without making a big mistake. Okay, so let's see. So we have to actually calculate rho and J, because that will depend on how the plasma responds. So let's see, mv dot is equal to minus EE. So this is electron equation of motion, right? I said there is no thermal motion, so there is no pressure gradient or anything. This is just, the right hand side is Lorentz force, and I'm actually ignoring V cross B by C, right? Because since I'm assuming V much less than C. So these electrons are non-relativistic, and in fact cold. So I'm actually taking V, thermal V. So I'm taking kT tend to 0. But electron velocity also, this velocity induced due to electric field is also small. So what it means is that even though electrons get accelerated by this electric field in the EM wave, it does not get accelerated close to C. Okay, so that's justified, and I will show that this is indeed the case. The velocity of the electrons is indeed much less than C. So we can actually ignore V cross B by C. And we know that for EM wave, E and B have similar magnitude in the CGS units. So V by C is much less than 1. So this is the electron equation of motion. Ion motion we are ignoring because they are very heavy. So V is equal to, again we assume the same form for everything, you know, the same form. So this is minus I omega due to V dot M equals EE. So, or minus EE, or V is equal to EE by I omega M. This is the velocity of electrons. And of course, it is varying sinusoidally at the same frequency as the frequency of the electromagnetic wave. What about, so this is V. What about J, right? J, the current density is equal to N electron number density times E times V, and with a minus sign because electrons have a negative charge. So E is absolute value of electronic charge. So so what do we get, which is equal to minus NE E squared by I omega M times E, right? So this is equal to J. This is the relationship between J and E, right? So J is equal to sigma E. This is the definition. This is how we define conductivity. This is plasma conductivity, electrical conductivity. So we can actually read off sigma. So sigma, you know, if we compare this and this expression, sigma is equal to I N E squared by omega M. So this is your plasma conductivity. Okay. Right. We also have the charge conservation equation, charge conservation, which gives us minus I omega rho plus I k dot j is equal to 0, or rho is equal to omega inverse k dot j. Which is equal to sigma by omega k dot e, right? Because j equals sigma e, and we are using a scalar conductivity. We are assuming that this plasma is isotropic. There are no large-scale magnetic fields and so on. So this is our rho, the density. In fact, this is density fluctuations. Right? This is charge density, right? So charge density is equal to the density fluctuations, because in a plasma, rho naught, the equilibrium charge density is equal to 0, because electron and ion quasi-neutrality. But this is the fluctuation actually. This is the fluctuation equation. So this is the delta rho. Okay. An electric field is the electric field in the field of the electromagnetic wave, which is also a fluctuation. Okay. Now what happens? So now we have, now we have rho and j that we were after, right? In terms of electric field itself. So our equation becomes, so we can actually put I K dot E is equal to 4 pi. Rho is equal to sigma by omega K dot E, or I K dot epsilon E is equal to 0, where we have introduced this epsilon. This epsilon is called dielectric. Yeah, this is the dielectric constant. Right, so D is equal to epsilon E. I K dot D is equal to 4 pi sigma free. So there is no free charge. All the charges that we have here are induced because of the electromagnetic wave. So this is a natural form of del dot D equal to 0. This is the dielectric constant, and we can actually just compare what is epsilon. Epsilon is equal to 1 minus 4 pi sigma by I omega. You can actually just see it from here, right? So 1 pi, so 4 pi by I omega. So you just divide and multiply by I, and you take I K dot E on the left hand side. So you have this, just by comparing. So this is your plasma dielectric constant, and you see there is an imaginary sign here. Okay. So this is the first equation that we had there. Of course, the second equation remains the same. Third equation also remains the same because we don't have the source terms. Fourth equation has a source term of J that we need to include. So what happens to the fourth equation? We can write it as I K cross B is equal to minus I omega by C epsilon E. The same epsilon, because now J here can be written as sigma E, and 4 pi by Cj is equal to 4 pi by C sigma E. So we have minus, so the right hand side of equation 4 is nothing but minus I omega by C E times 1 minus C by I omega four pi sigma. So 4 pi by C J, 4 pi by C sigma E. So right hand side becomes minus I omega by C E times 1 minus 4 pi by C. So anyway, so we get this form, which is nothing but now we have replaced the vacuum. No, so now we have the vacuum form of electromagnetic equations, right? Because the source terms, the rho and J terms, have been absorbed into epsilon E. Now again, right, K dot B is 0. That means B is transverse to K. K dot E is also 0 because epsilon is a number. So K is E and B are perpendicular to K. Similarly, this equation says that K is perpendicular, E is perpendicular to B. So basically K, E, B again form a triad as in vacuum. So, if this is K, E, this is B. Okay, and what about the dispersion relation? What about the equivalent of this equation? Let's see. So these two equations remain the same. And we have 1 and 4. So what do? We do, K cross. So iota K cross K cross E is equal to iota omega by C K cross B. So this is equal to so K dot E, K is 0, so this is minus I K squared E is equal to I omega by C. So omega by C, K cross B, I K cross B, we can actually just substitute from this equation. I K cross B is minus I omega by C epsilon E. So we get our dispersion relation. We get omega square epsilon is equal to C squared K squared. This is our dispersion relation in presence of plasma effects. So it looks very, very similar to the other one, except that there is an epsilon here, right? And what is the value of epsilon? Let's see. Where did I? Yeah, epsilon is this, right? So sigma is that. So this is equal to, let me just write down in color. This is equal to 1 minus. So if we substitute for sigma, we get iota cancelled. So this is equal to 4 pi Ne E squared. So Ne is the electron number density divided by omega squared, which is equal to 1 minus omega p squared by omega squared, where we have introduced omega p as the plasma frequency. 4 pi Ne E squared by m. This is the plasma. This is electron plasma frequency. So this is an important relation. So this is the plasma dispersion. This is the plasma dielectric constant for this particular isotropic unmagnetized plasma. Okay, so what about the relationship between omega and K? So what do we get? So if we substitute for epsilon, we get omega squared minus omega p squared is equal to, so I've just substituted for epsilon here. I get omega squared minus omega p squared is equal to c squared K squared, or K is equal to omega p squared, omega squared minus omega p squared 1 by c for omega greater than omega p. What happens for omega less than omega p? See, whenever you have, whenever you consider, some wave moving or refracting through a medium, right? Omega remains the same on refraction. K changes, right? Because omega is just decided by how fast the source which is producing radiation is oscillating, but K is determined by this dispersion relation. So omega is fixed, but K adjusts to satisfy this relation in both media. So what does it mean? What does it mean? When omega is less than omega p, this thing under square root becomes negative. What does it mean? Can someone tell me? We have actually encountered this in metals. This is a hint. Can someone?
I think this is means decaying of electromagnetic wave means.
Yes, this is the attenuation of electromagnetic waves when it tries to enter a conducting medium. Right? This is the reason. This is the reason why metals are so shiny, that the electromagnetic radiation is reflected from it. Okay, so plasma medium is sort of like metals because electrons are free and very mobile. Okay, the plasma is very conducting, easy to polarize it because charges are just sitting there ready to move to every electric field that's applied. Okay, good. So let me make some space here. This is very important and useful and actually simple formula. This explains how how waves travel, electromagnetic waves travel through a plasma. Okay, let's see. So if we substitute the numbers, we get omega p is equal to 5.6 times 10 to the 4 n to the 1/2 per second. This is the plasma frequency. If we put in the values for all the constants, 4 pi n naught e squared by me, square root of that. So if omega is less than omega p, what we have is K is equal to iota by C omega p squared minus omega squared. Now this quantity in square root is positive, and we have e to the minus I omega t plus I k dot r. So you have this goes as e to the minus I omega t minus omega p squared minus omega squared by c times x, so or times z if you're moving. So this is along k, along the direction of incident wave. Okay, so this is the attenuation that we were talking about, attenuation in the plasma for omega less than omega p. And right, the length scale for omega p is much greater than omega. The length scale over which this attenuation happens is just 2 pi by k. Attenuation length is 2 pi by k, which is omega p c. Okay. Now Earth, this is very important implications actually. This fact that waves are reflected by a plasma has important implications because Earth has something called an ionosphere. So above the atmosphere, because of ionizing radiation coming, or because of particles hitting the Earth, there is this layer of the Earth that is ionized. Okay, and the number density there is about 10 to the 4 particles per centimeter cube. So what happens to the plasma frequency? So omega p is roughly, so this is 100, 5 times 10 to the 6 per second. So frequency is 2 pi. So omega by 2 pi. So frequency is about 10 to the 6 per second, which is like a hertz, a megahertz. So what does this mean? So if you have Earth and if you have ionized plasma here around it, and if you have some electromagnetic wave coming, if it has a frequency less than 1 megahertz, it will just be attenuated in this direction, it will be reflected, right? So, basically what it means is that you cannot do radio observations less than megahertz from Earth. I mean, a lot of early radio transmission, radio communication relied on the ionosphere. So they would send radio waves and that would get reflected and received elsewhere. Okay. What else? The other thing to note is that this J and E are out of phase because sigma is iota. So J, so this implies that J and E are perfectly out of phase. So basically they are like sine and cosine. So if you multiply sine and cosine and if you average them, right, you get 0. Sine phi cos phi is equal to 0. So that means on average there is no work done by electric fields on the plasma or vice versa, because J dot E is the work done by field on the plasma and vice versa. So since J dot E on average is equal to 0, there is no dissipation in the plasma. Okay. So now I have a question. Okay. The question is, we know so this is the surface of the Earth. We know that there are layers of the ionosphere which have certain density as a function of height. I want to know this electron number density as a function of height. I want to know Ne as a function of Z. How would I do that? Can someone suggest? Right? So you heard the theory. Now I want to test, like, at what height is this layer with this electron number density located? How can someone suggest me how one can go about this? Let's see.
Some maybe e to the power that minus kz means tending to 1. Then
right. So that is fine. Basically what you can assume is that at whatever height omega is equal to omega p, the wave is reflected, right? What happens is when omega is equal to when omega is less than omega p, at that height, the plasma wave gets reflected. So Sachin, can you try to construct how we can try to do this? So basically, yes.
So we have means when we write e to the power iota kx minus omega t, and have k as imaginary, means so we from the k factor we will get some e to the power minus 1 by c omega square p minus omega square z. When this z means we can compare it to when it is getting close to 1, maybe.
I mean, even simpler, right? So what I'm saying is, you have some, say, suppose here, here the electron density is say 10 to, say 10 to the 4 was like an average number. This is 10 to the 4. Let's say here it is 10 to the 3, and here it's 10 to the 5, right? So how would you do that? So 10 to the 3 corresponds to some omega p, right? If you launch this wave at this frequency, it's reflected. So you can measure the travel time because it's almost vertical propagation if you consider. You measure the travel time. So twice h by c, right? This is the travel time. And omega is equal to omega p. So the travel, so if you have higher frequency, it propagates deeper. So if you send a higher frequency wave, it goes till here and then comes back here. So this will take a longer transit time. This will have a higher height at higher frequency because it reflects at a difference. So this gives you a way to measure. So this time, basically echo time gives you a way to measure height of different layers. Okay, do you get the idea, Sachin?
Yes, sir.
Right, so basically this is how you can probe the fine structure of the ionosphere, for example. And then the ionosphere is actually very, very interesting. There are like interesting layers, there's F layer, G layer and whatnot. So people have actually measured this substructure very carefully. It is also highly time dependent. The ionosphere, the ion abundances and ionization and so on can actually depend on space weather. If the sun is very, very active, there can be huge fluctuations on the ionosphere. So right. So this is quite interesting application. Okay, what else? Let's see. What about the phase velocity of these waves, right? So we have omega square equals omega p squared plus c squared k squared, right? What is the phase velocity of these waves? Phase velocity is just omega by k hat, right? If you take it as a vector. This is the velocity with which the phases move. So, right, and we know, so this is equal to omega divided by, now k is equal to omega squared minus omega p squared. C, right? So this is the phase velocity. So this is equal to C by 1 minus omega p squared by omega squared. So you see the phase velocity is greater than c, right? Because 1 minus omega p squared by omega squared is less than 1. So c divided by something which is less than 1. So phase velocity is greater than c. What about the group velocity? Right, so basically you know the difference between phase velocity and group velocity, right? So if you have a wave packet of waves, right? So you add up a bunch of different k's and form this wave packet. Now this packet as a whole moves at the group velocity, but these individual crests, this crest for example moves at the phase velocity, right? But the energy and information propagation time is the group velocity. Phase velocity really doesn't mean that, the large phase velocity doesn't mean that information is propagating faster than speed of light. So Vg is equal to d omega dk. This is your group velocity. So how do we get this? Right, so this is equal to, so like, let's say, so omega is equal to, omega squared equals omega p squared plus c squared k squared. And let's consider just 1D propagation. So twice omega dow d omega dk is equal to c squared twice k. So that gives you, so you get d omega dk is equal to c squared k by omega, and that's nothing but c squared by v phase, right? Omega by k is v phase, so this is equal to, so this is equal to vg. So vg is equal to c squared by v phase, so this is equal to c times 1 minus omega p squared by omega squared, which of course is less than c, as it must be. Right, so this is the group velocity. So do you understand this difference between group velocity and phase velocities, people? Is there anyone here who does not know the importance of the distinction between these two velocities? Let's see. Buana, you know the difference between phase velocity and group velocity?
Yes, sir.
What is it?
Group velocity is the velocity at which the whole packet of wave is traveling, and phase velocity is the individual amplitude or the crest is traveling.
Okay. So, do you know of some waves for which group and phase velocities are different?
Um, uh,
Some
I
No?
I can't think of.
So, for example, if you drop stone in water like a pond, you see there are waves, right? So those waves, the surface gravity waves, have different group velocity and phase velocity. Okay.
Yeah.
There are things called internal gravity waves. They have different phase velocity and group velocity. In fact, their group velocity is perpendicular in direction to their phase velocity. So this is a very, very important concept. All of you should be aware of it. Okay, good. So what does it mean that the last part of this class? So let me just say pulsar dispersion. So the pulsars, there are objects called pulsars, and they they are rotating neutron stars, and they sort of emit very regular pulses after a very, very constant time. So you have this pulse of emission, intensity as a function of time, and it sort of keeps repeating and so on. Okay, so sometimes you may miss it, and sometimes its amplitude may be distorted, but whenever at this, if you see a pulse, it will almost always be at the same phase. Okay, so if you have a pulse of radiation, this is sort of like a wave packet, right? This is in time, so you have a pulse in time, so this is sort of like a wave packet, and it has it has some intensity of the electric field varying like this. Okay, and right, so we know that so this tau, this width is like scales like 1 over delta omega, right? The bandwidth and the duration of this pulse are inversely related like this. So longer the pulse, smaller is the bandwidth, right? You can, when we consider plane waves, infinite plane waves, their delta omega is 0 because you only consider a fixed omega naught, right? So this is sort of a pulsar electric field, for example. Now, right, so suppose you have a pulsar which is emitting pulses from here. Okay, and you know you are an observer who's seeing from here, and so what is the propagation time? So propagation time, propagation time of this pulse is equal to. So if this object is at a distance d, is equal so this is ds by vg, right? These pulses at different frequencies. So this pulse looks slightly different at different frequencies, right? Because this pulsars are broadband emitters, so their delta nu is actually pretty big, is big. So in fact they emit more. They are more luminous at low frequencies. So this is the propagation time. So this is the differential distance ds, and vg is the group velocity at that particular frequency of pulse. This is propagation time of a pulse at a given frequency omega. Okay, so and we know this group velocity here. We have actually calculated it. So this is our propagation time of a pulse. This pulse moves at the group velocity, right? That's what the velocity with which energy moves. Let's see. What is Vg inverse? That's what we need, right? Vg inverse. And we are considering 1D propagation, so this vector signs don't mean much. So Vg is equal to c times 1 minus omega p squared by omega squared to the power of a half, right? And generally speaking, omega p is actually much less than omega, right? Because so we omegas are of order, we are measuring these at 100 megahertz, right? And we know that omega p, like even for number density of 1, it's 10 to the 4, right? Which is much smaller than megahertz. For the ISM density, number density, and ISM of electron density is about 0.03 particles per centimeter cube. So omega p is actually much less than omega. Okay, so this actually can be approximated as using binomial expansion. So this is 1 minus omega p squared by twice omega squared. Okay, so this is this Vg inverse which appears at the bottom. So this propagation time is equal to integral 0 to d ds by c, and again we can apply the this sorry, this is E inverse. This is minus, so it becomes plus, right? So because I had 1 by Vg, so this is C inverse minus a half, right? So this is equal to C inverse times 1 plus omega p squared by twice omega squared. Okay, so this is your this is what this is equal this is equal to d by c. The first term just gives you the distance divided by speed of light plus, and what is, so this is 1 by 2 omega squared. Omega squared, if you recall, is 4 pi ne e squared by me. ds, right? So this is what you have. So this is propagation time for a frequency omega is given by this, and this is equal to d by c plus 1 by twice omega squared 4 pi e squared by me integral ne ds. But you can have like a different electron number density along the line of sight. You can have a dense region and a dilute region and so on. This is just a line of sight integral. Okay. Okay, so this is the arrival time. So this is the time travel. This is the travel time from the pulsar to here. Okay. Right. So this is pulse arrival time. So now the question is, if omega is larger, so larger omega implies that this correction is smaller, right? So it takes longer for lower frequency, longer time to arrive. So we can actually calculate dTp omega by d omega, right? How much does the arrival time change as a function of frequency? This is equal to minus 4 pi e squared by mc. I think I missed a c. 4 pi e squared mc omega cube. Right, I'm just differentiating with respect to omega times this dispersion measure. So this d is called dispersion measure, and it's defined as integral 0 to d ne ds. Okay, so this is just the line of sight integral of electron number density, and this is typically measured in parsec per centimeter cube. Right? This is a natural limit because the length scales that you travel are of order parsecs, and the number density is like 0.01 per centimeter cube. So this is the same as unit wise. It's the same as per centimeter square, but this is more user friendly, parsec per centimeter cube. Okay, so what does it mean? What it means is that the arrival time is shorter for higher frequencies. So omega high TP is low. So low frequency waves arrive, or pulses, not waves, let's call them pulses, arrive later. So let me actually show you an example of this. This is a real effect, and you see it in pulsar. So here is an example of a pulse from a pulsar. Okay, so you see this high energy, so high intensity for some time and then nothing. And this is the observed frequency, and this is the phase. So you see at high frequency it arrives early, right? At like 380 megahertz it arrives at this time. At 320 megahertz it arrives at this time, and so on. So you can actually see this bright thing. This shows this pulse. Okay, so this pulse at 370 is here, but at higher and at lower and lower frequencies it arrives later and later. Okay, so this is called the dispersion, the pulsar dispersion, and this is actually this is the pulse arrival time relative to the speeds, relative to the vacuum as a function of frequency. It's the same thing that I had there. This is just This is just this expression 1 by omega squared. Okay, so these are actually very, very important effects. And we will actually continue with this in the next class. Any question? Otherwise, I will end the session. Okay.
So here, any consist of all the means material in the way of the pulsar that is there. Pulsar coming from some extended source.
No, pulses are coming from a pulsar, which is not an extended source, but it is traveling through a large medium. So it will travel through neutral part and ionized part and whatnot. So it will be a line of sight integral of all that, which adds up. So what is important is integral any dl. It may be distributed in different ways. You can have very high electron number density somewhere and nothing beyond it. It is really the integral which matters for the total delay time, arrival time of the pulse. Okay.
Okay.
Okay, we'll
Yes.
continue in the next class.
Thank you, sir.
Okay, thank you.